Chapter 7.1 Monosaccharides and Disaccharides. Chem 7784. Biochemistry. Professor Bensley. Chapter 7.1 Monosaccharides and Disaccharides. Today's objectives: to learn and understand their structures and names of monosaccharides, open chain and ring forms of monosaccharides, structures and properties of disaccharides, aldoses and ketoses. An aldose contains an aldehyde functional group. A ketose contains a ketone functional group. Figure 7.1e representative monosaccharides. A two trioses, an aldose and a ketose. The carbonyl group in each is shaded. Enantiomers. D-glucose and L-glucose are enantiomers, non-superimposable complete mirror images, differ in configuration at every chiral center. Diastereomers. D-threose. D-erythrose. Epimers. Epimers are two sugars that differ only in the configuration around one carbon atom. Figure 7.4 Epimers. D-glucose and two of its epimers are shown as projection formulas. Each epimer differs from D-glucose in the configuration at one chiral center, shaded pink. Structures to know: ribose is the standard 5-carbon sugar. Glucose is the standard 6-carbon sugar. Galactose is an epimer of glucose. Mannose is an epimer of glucose. Fructose is the ketose form of glucose. D-ribose, D-glucose, D-galactose, D-mannose, D-fructose. Hemiacetyls and hemiketyls. Figure 7.5 Formation of hemiacetyls and hemiketyls. An aldehyde or ketone can react with an alcohol in a 1:1 ratio to yield a hemiacetyl or hemiketyl, respectively, creating a new chiral center at the carbonyl carbon. Substitution of a second alcohol molecule produces an acetyl or ketyl. When the second alcohol is part of another sugar molecule, the bond produced is a glycosidic bond, p. 243. Cyclization of monosaccharides. Pyranoses and furanoses. Figure 7.7 Pyranoses and furanoses. The pyranose forms of D-glucose and the furanose forms of D-fructose are shown here as Haworth perspective formulas. The edges of the ring nearest the reader are represented by bold lines. Hydroxyl groups below the plane of the ring in these Haworth perspectives would appear at the right side of a Fischer projection. Compare with Figure 7.6. Pyran and furan are shown for comparison. Chain ring equilibrium and reducing sugars. Figure 7.10 Sugars as reducing agents. Oxidation of the anomeric carbon, and probably the neighboring carbon, of glucose and other sugars under alkaline conditions is the basis for Fehling's reaction. The cuprous ion, Cu+, produced forms a red cuprous oxide precipitate. In the hemiacetyl ring form, C1 of glucose cannot be oxidized by complex Cu2+. However, the open chain form is in equilibrium with the ring form, and eventually the oxidation reaction goes to completion. The reaction with Cu2+ is complex, yielding a mixture of products and reducing 3 moles of Cu2+ per mole of glucose. Important hexose derivatives. Figure 7.9 Some hexose derivatives important in biology. In amino sugars, an N.H. 2 group replaces one of the O groups in the parent hexose. Substitution of H4O produces a deoxy sugar. Note that the deoxy sugars shown here occur in nature as the L isomers. The acidic sugars contain a carboxylate group, which confers a negative charge at neutral pH. D-glucono-delta-lactone results from formation of an ester linkage between the C1 carboxylate group and the C5, also known as the delta carbon hydroxyl group of D-gluconate. The glycosidic bond. Figure 7.11 Formation of maltose. A disaccharide is formed from two monosaccharides. Here, two molecules of D-glucose, when an O, alcohol, of one glucose molecule, right, condenses with the intramolecular hemiacetal of the other glucose molecule, left, with elimination of H2O and formation of a glycosidic bond. The reversal of this reaction is hydrolysis, attack by H2O on the glycosidic bond. The maltose molecule, shown here as an illustration, retains a reducing hemiacetal at the C1 not involved in the glycosidic bond. Because mutarotation interconverts the alpha and beta forms of the hemiacetal, the bonds at this position are sometimes depicted with wavy lines, as shown here, to indicate that the structure may be either alpha or beta. Non-reducing disaccharides. Two sugar molecules can be also joined via a glycosidic bond between two anomeric carbons. The product has two acetyl groups and no hemiacetals. There are no reducing ends. This is a non-reducing disaccharide. Examples: sucrose and trehalose. Structures on next slide.